Welcome back to Maths in an Empty Classroom with me, Mr. Southern. This is part 2 of the lesson on further differentiation applications, and in this video I'm just going to be going through an example where x is defined in terms of y. It's a more complicated function. So here we have a curve has equation x equals 4y tan 3y, so we can see how rather than it being y in terms of x, it's x in terms of y. We'll just have to consider how we deal with that as we work through the question. We're being asked to find the equation of the tangent to the curve at the point where y equals pi over 3 in the form ax minus b pi y plus c pi squared equals 0, where a, b and c are positive integers to be found. So we're being given a very specific form for our final answer here, which we'll get to as we work through. So okay, we have x equals 4y tan 3y. And finding the equation of a tangent, we're going to differentiate, but what we just have to be aware of is when we differentiate this function, rather than getting dy dx, we're going to be getting dx dy. We've got the product of two things here. We've got 4y, so we're going to call that u, and then we've got tan 3y, which we're going to call v. So differentiating both of these in terms of y. So we're going to get du dy equals 4, and we're going to get dv dy equals 3 sec squared 3y. So tan differentiates to sec squared, so tan 3y differentiates to sec squared 3y, and we multiply by 3 because of the chain rule, that function 3y. Now we're going to use the product rule. We've just got to be a bit careful how we write this because it isn't dy dx, it's dx dy. So it's v, and rather than du dx, it's du dy, plus u, and rather than dv dx, it's dv dy, because all the expressions we're using here are in terms of y. So v du dx, that is going to be 4 tan 3y, plus u dv dx, that is going to be 4 times 3 is 12y sec squared 3y. I'll just write again so that we don't forget that this is an expression for dx dy. Now to find the gradient of the tangent at the point that I've been given, I need dy dx, I need the value of dy dx because that's the gradient of the tangent. And what a lot of students are tempted to try and do now is to flip this expression to get dy dx. Don't do that. Substitute in the values, and it's much easier to flip a number than it is to try to flip a function. So at this point here, I've been given that the y coordinate is pi over 3, so I'm going to substitute y equals pi over 3 into dx dy to get a numerical value for dx dy. So 4 tan 3y, I've got 4 tan 3 lots of pi over 3 plus 12 lots of pi over 3, and then sec squared 3y. Now thinking about what sec squared is, it's 1 over cos squared, so it's 1 over cos 3 lots of pi over 3, so I'm just going to write pi, and then that is squared. So you work out cos 3y and then you square it. So let's have a think about what we get here then. So 3 lots of pi over 3 is pi, and tan of pi is 0. No, it's not. Tan of pi is... Yes, tan of pi is 0. Yes, it is. Tan of pi is 0. Brilliant. So we're going to get 0. Lovely. And then we've got 12 lots of pi over 3, so we've got 4 pi there. Cos pi is negative 1, squared is 1, so that's all being multiplied by 1. So actually what we're getting as our value of dx dy is 4 pi. Just going to check that. I'm always telling my students they should know these. Cos pi negative 1. Yeah, there we go. So 4 pi. The gradient of the tangent is the value of dy dx at the point, So dy dx at this point is going to be 1 over 4 pi. And hopefully what you could see is it was so much easier to substitute in the value and flip the number than it would have been to try to flip that function, particularly with that plus in the middle. It wouldn't have just been a case of saying 1 over this plus 1 over this. That is hideous, illegal maths. Please don't do it. In addition to the gradient, I'm also going to need the x coordinate because I'm given that y equals pi over 3, and I need to use my original function, which is x equals 4y tan 3y, and substitute pi over 3 into here. Like so. Okay. So 4 lots of pi over 3, but tan of pi is 0. So this is going to come out as 0. So the coordinate that I'm using is 0 pi over 3. And I have that the gradient of my curve is 1 over 4 pi. So cracking out the general equation of a straight line, y minus y1 equals m bracket x minus x1. Y minus pi over 3 equals 1 over 4 pi x minus 0. Now this is the point where I always say to my students, this is why you must use this as the general equation of a straight line rather than y equals mx plus c, because it makes dealing with gradients like this much easier, because we can multiply through by 4 pi to get 4 pi y minus 4 pi squared over 3. Now that's important. When we multiply pi by 4 pi, we're going to get 4 pi squared. Pi squared is a number, but we're going to leave it in terms of pi. And that is just going to equal x. Now let's just look at the form that we've been asked for. We've been asked for ax minus b pi y plus c pi squared equals 0, but crucially a, b and c are positive integers. So what I need to do is keep the x as positive, subtract the 4 pi y, this is looking good, similar form to what we've been asked for, plus 4 pi squared over 3. Now we were told that a, b and c all had to be integers, so I'm going to multiply through by 3 to get my final answer, 3x minus 12 pi y plus 4 pi squared, which means that I can state my values of a is 3, b is 12, and c is 4. Now b is 12 because in the form given it was negative b pi, so if negative b is negative 12, b is 12. So there we are, there's the equation of the tangent to the curve. So differentiating x in terms of y, I think the most important point you can take from that is once you've got your expression for dx dy, substitute in the values and then flip the number, don't ever try to flip the function. Okay, job done.